No, it was just for English, for lectures in English. Yeah, I
So
just
you
found
are
out to
formally
raise my
registered.
hand.
You're formally registered to the course.
I think so, yeah.
Okay, so we'll give it in English. So now everybody would love you. No, I'm joking. I mean, okay, this is fine. So what is this course all about? This course is about understanding what is a signal and then ways to process it. And in a sense, it would be an introduction to, I mean, there is a big elephant in the room, which is called deep learning. Deep learning basically revolutionized everything we do in computer science, at least in the applied sense, in the sense that we no longer, at least in computer vision and natural language processing, we no longer try to find a model for the problem, but rather find a way to feed a lot of data into a specific architecture. Think about it as a lookup table. And the lookup table should be able to find out the relations, not finding out, I mean, somehow code the relations between data and the annotations of the data. So if you have a specific symptom that would indicate a specific illness, the lookup table would know how to look at the symptoms and output the specific illness, the specific pathology that you exhibit given those symptoms, okay? The question is how to get there is complicated. Now, roughly speaking, in this field, what can be done is given something which is non-convolution, the network can somehow utilize this notion and learn a lot of parameters using a property which is called linear shift invariant. Now, it is true that the convolution was adopted also to the field of natural language processing and others, but the core assumption, or if you have an image and a face can appear at that point or that point, you would like to apply the same operators in order to find the face in the image, or if you have, I don't know, a cat, so it's no longer a face of a person, but rather a cat, you should apply the same filters, the same operators in order to detect the cat here or there. If you have a time axis and you have a sound that is playing and you would like to identify a word, then you should probably apply the same filters at the beginning of the signal or the continuation of the signal in order to detect a specific word. Okay, so if you have this nice property of being invariant, independent of the place of the location in the image or the location in time or the time that you're looking for the phenomena, then you can utilize this notion of convolution. In this course, we will learn the origin of convolution. It appears to be that this notion is really nicely, can be nicely treated and analyzed from a point of view, from a mathematical point of view, and it would immediately give us the intuition behind what can be done with this kind of, let's call the white elephant in its name, these CNNs, okay, this convolution neural networks, okay. It would also give you an intuition and introduction into the next step of what happens when you don't have this linear shift invariance. So in NLP, they more or less force convolution into the structure of what you're doing, but the question is, what can you do if you don't have this property? And for that, this is something that goes beyond this course. You will have to resort to, I don't know, to manifold learning and other courses, one of them that I'm also giving together with Ronan Talmon from the EE department. So with Talmon from the EE department, we are giving a course which can be considered as a continuation of this one, although this course is not a prerequisite of that course. Okay, so now what you will have to do is submit homeworks. You will have about, as far as I recall, four homeworks. I think, and Tom, please correct me if I'm wrong, it should be about 30 or 40% of the final grade. You could do it in pairs, and then you will have a test. At the end, the test would account for about 70% of the grade, And in the test, you will have to perform, I mean, it would probably, I mean, surely verify that you did your homework and push it one bit further so that it would evaluate how well you have been acquainted with the material that I'm teaching you in this course. Now, the course would involve we'll start with really trivial ideas. I mean, what can we say about representation of objects or points in the most trivial sense? I mean, if you have points, objects, I don't know, numbers on the real value, how can you represent them in the best possible way? Okay, so the question is, what is the meaning of represent? What is the meaning of best? What is the meaning of way? And this would account for if you have a single representation for your values. Okay, assume that for these points in the plane, you have selected this one to be your representative, and for these numbers on the real line usually we denote as R. Points in the plane, Euclidean plane, for example, will define as some points that belong to R2. So these would be values on the real number, and these would be values on the real plane. And the question is, what would be the best possible way of looking at this number would be the issue during the first lecture. Then we'll start asking the question of, okay, assume that you have not only a single number, but a small set of numbers by which you can represent your set of blue points here, or your set of numbers here. And the question is, what would be the best way of distributing these, let's call them representative numbers or representative points or representative objects that would best fit into, and again, the question is what is best, into this set of blue numbers that we have. Then what we'll do is we'll try to go into more complicated scenarios, and this is not treating just points in R2, but rather, first of all, a function. We'll call it phi of t, and t would be my time, for example, and say that the time is bounded. I mean that I'm looking at my functions at a given interval. We denote this interval by delta. And then the question would be, what would be the best function that would the best, for example, at the beginning, the best constant, and then the best set of functions that would represent my function. Now, then comes the issue of what can I use in order to make my selection of a constant representative or a set of functions as a representative in the best possible way. And then would come a little bit, it would not be a course about statistics, but it will be a little bit about probability and statistics. Those of you who are really afraid of probability, this is not a course about probability, although what we will do is use the first and second order moments, or the expectations of a number, of a random number, in order to make some claims about the functions that I'm about to represent. Any of you heard about eigenfunctions or eigenfaces or eigenimages? Just raise your hand. Okay, so there is at least one. So eigenfunctions is one such example. We will talk about, I mean, in this course, we will talk about PCA, principal component analysis, and when we'll get there, you will see how PCA relates to everything that we are talking about in this course. We'll talk a little bit about Fourier. For example, it appears that Fourier is intimately related to convolutions, okay? And we will learn about this intimate relation. And the moment we learn about Fourier, convolution, and representation, the question that comes to mind is, in what sense the Fourier is optimal? I mean, we heard about Fourier. I mean, Fourier is some way of representing functions. I mean, and if you haven't, you will learn about it in this course. And the obvious question that would come in mind would be, assume that I'm allowed to describe my signals with only 3 sine waves. In what sense am I optimal? And it appears that there is a beautiful and nice relation that we will learn about that would tell us in what sense we are optimal. So this would be Fourier. And in fact, it gives a really nice relation between PCA and Fourier. So convolution would relate to, in some sense, into the deep neural networks that CNN, or you call it DNNs, the deep, that you will use in other courses. And this is why this is an introductory course rather than a course about deep learning. But at least in this course, you will understand what is going on in the first common layers in a deep network scenario. So in a deep neural network, what happens is that you have your input. These are, for example, the coordinates of your points or your whatever. And then you have something which is called some layers that are connected to one another. And this is why it is called deep. And along the way, there are some ReLUs, I mean, some way of truncating the negative values, and some fully connected and not fully connected. And at the end, what you have usually is something which is called a fully connected network, or something that by which you can make the decision. Okay, so this is the decision-making part of the network. So if you understand where convolution is coming from, you will have intuition of why this part is so important and why it is using convolutions. But again, this course is not about convolutions. It's about explaining and giving the motivation of how to represent objects, numbers, and in the end, how to denoise images, for example. Okay, so let's start from the most basic idea, and this is the idea of how to think about numbers. So assume that somebody is giving you a set of numbers. Okay, so these numbers are given as a set. Okay, so I can represent them as xi, where I goes from 1 to n. And assume that some oracle is also ordering these, and these numbers are part of the real numbers. So they are they are taken from, I don't know, minus 1,000 to plus 1,000. So I also limited the domain at which we are observing. And assume that some nice oracle also ordered them, so that what I know to say is that xi is smaller than a and then xi plus 1. Now, a question to the audience: who knows what is the complexity of ordering a set of n numbers? I mean, most of you should be familiar with that because you took Introduction to Computer Science. But what is the complexity of ordering a set of numbers? Yes.
N log n.
So Dan, yeah, sorry.
N log n.
N log n, yeah. And can you do better than n log n? So it's n log n because
currently no, based on what they taught us in introduction.
It depends on the range of the data. You can do bucket sort in all of n.
So Liran is saying that it depends on the data. Well, if you quantize your data, then yes, you would be able to do it in n using bucket sorting. But for now, I'm not giving you any quantization of the data. In fact, we will result to quantization and we'll ask how to quantize the data. So for the time being, in fact, they proved to you that you cannot really do better than n log n. So this is the best you can do when you'd like to order arbitrary numbers. Okay. The next question that comes in mind, so somebody ordered the numbers, and then the question is, how should we represent these numbers? And if we go to the dictionary, we say that we see that the definition of ordering is to stand for, to act as substitute, to depict, to describe. What we would like to do is somehow find a representative number. Let me just control the errors that will refer to as come on. Well, let's do that. That will denote as theta. Okay, so this theta would be my representative number. And immediately I will delete all the errors. And what I will try to do is say that this theta is a representative of all my numbers, and then the error of representing all the numbers by theta is, say, the subtracting theta from each and every one of my given numbers. Okay. And what we'll do is we'll denote the error of representing xi by theta as epsilon of I, or the error I. Okay. And now the question would be, how should I represent my numbers using this kind of thetas? Anyone has any idea? Suggestions, please raise your hands. Yeah.
Floating
so
point
this
number.
Is, so who, Michael, yeah?
Yeah,
Okay, so what is
So-
the idea?
so we can make an average of all the numbers and make the theta this average.
So Michael is suggesting to use the average so the average is summing over all my xi's and dividing, for example, by 1 over n, and this should be my theta. Okay, this was your suggestion?
Yes.
Okay, so selecting the average as a representative number should be one option. Is this a good option? So let me give you an example. Assume that you are an employee, for example, in Apple. Okay, and usually we know that engineers, especially computer scientists that work in Apple, get huge salaries, probably twice as much as the rest of the engineers in the world. The question is, would the average of all these salaries represent the salary of an arbitrary employee in Apple? What do you think? Let me give you the answer. The answer is no.
No.
In fact, if you average the salaries of all incomes, and let's not call it salaries, but rather incomes in Apple, you would see that the salary would be, the average salary would be higher than most of the salaries. It would be more or less equivalent as asking what is the month at which all women are pregnant. I mean, assume that you are looking at the average of the pregnancy duration of all the women on the world. On the average, you would get that every woman is more or less at the first month of her pregnancy, which would probably not be the correct answer. So averages are good, but they are good with respect to a specific way of measuring a penalty. And for that, what we'll need to do is define somehow the penalty. So what we will do is mathematically define a function of the errors by scanning through all my errors, why is it not writing here? Let me just try to do that. All my epsilon i's. And we call it a quality measure. Okay, so the quality measure is denoted as psi. And this psi would get as inputs all the errors, the subtracting of theta from x1, from x2, etc., etc. And what I would like this measure function to be is I would like it to have the following properties. So if I'm taking the absolute value of the errors, I mean, I don't really care if the error is positive or negative, then what I would like to, the properties that I would expect my quality measure to have is to have the lowest possible value when all the errors are 0. So I would expect the best possible quality to have the lowest value. So in fact, when I'm talking about quality, in that sense, I would like the lower the value, the better the quality. Okay, this is just to confuse you or myself. Then what I would like to have is that if I'm increasing each and every variable, so assume that I'm considering the nth variable of this function, which would be epsilon n, and I'm increasing it, I would like my quality measure also to increase. So if I'm taking the derivative with respect to each and every element of this function, I would like the derivative with respect to each and every element to be higher than 0. It means that if I'm looking for a specific function, it should assume that I have a single variable, it should decrease to 0, and this is where epsilon is equal to 0, and then it should increase when epsilon is higher than 0. Okay, so for all positive points, okay, so if this is epsilon, and since we're taking the absolute value of epsilon, it should actually have this property of looking at my, let's call it psi, okay, of looking only at positive psi's, and always decreasing when psi decreases and always increasing when psi increases, okay? What I also would like is to have that if my psi's, if my entries to the functions are always positive, I would always like my my function to be higher than 0, okay? So this is for all points which are positive. This is how I define the points to be positive. So if R would have been my real value, when I'm considering only the positive values excluding 0, I'm calling it R plus. Okay, and R plus n means that I'm looking at, this would be R2, excluding the 0, and I'm adding my accesses to denote that I'm looking only at positive numbers. So I would like my quality measure to always be higher than 0 if the points are not equal to 0, and only if all points are equal to 0, I would like my quality measure to be equal to 0. So the question is what kind of important functions we can look of. And the first example that comes to mind would be, for example, what would happen if I would, let me just see if I can. Yeah. So what would happen if I'm taking this function? Hope that you can see that my video is not overlaid on that. And this is called the mean squared error function, because what I'm taking is I'm summing over all my errors over the squared value of all my errors. So what would be the optimal theta in this case? Anyone has any idea?
The mean.
Who said the mean? Okay, so Barak Gur said the mean. Thank you, Barak. And obviously, this is a very trivial example. So this is called, let me just bring this slide. So this is called the mean squared error loss, okay, MSE. So M goes to mean, just remove that. So M goes to mean squared error loss function. And it sums over all the difference between each and every xi and my representative number. And what can I say about this function? It's also called L2 because if you think about the if you think about the entries of my function, then you can think about it as epsilon 1 being the first error, the first coordinate. Let me do it in another way. Assume that I have this would be x1, this would be x2, this would be x3, and my psi here can be thought of as a vector. Okay, it's a vector that that sums up whose length, okay, is nothing but epsilon 1 squared plus epsilon 2 squared, etc., etc. Okay, so this would be the length or the squared length of this vector, and this is why we call it L2. Okay, L2 means that we are summing over the coordinates. So in that case, it would be this coordinate. Let's call it epsilon 1 squared. If I square the coordinate plus epsilon 2 squared plus epsilon 3 squared, this would be the L2 error. This would be the L2 measure of the length of this vector. And there are other measures that we will talk about. Okay, so we have this loss function, and this loss function is can be minimized in order to find the unique minimizer for theta. So let's do that. Let's find a way of minimizing this function. So what we do is we take the derivative with respect to theta of the MSE function, And if I'm taking the derivative of, let me remind you, it was sum over xi minus, come on, minus theta squared, it would be nothing but 2 times 2 times xi minus theta. Okay, and now I can, I mean, you can immediately see that if I equate it, make it equal to 0, then summing over the thetas, I mean, if I sum over all the thetas, I can in fact take the theta out of the sum, and thereby I'm summing over 1, and this would give me n times theta. Okay, so if I now equate it to sum over xi, the result would be that I'm getting the average summing over all the xi's as my theta minimum. Okay, so this is a trivial idea. I wasted, in a sense, half an hour of your time and my time in order to show you that minimizing the L2 error would give us nothing but the average, which is almost obvious. But in a moment, we'll see that things are becoming a little bit more complicated when we complicate things, okay, which is obvious. For example, I told you that if I would like, for example, to compute the average of all the salaries, I would like to find a different way of thinking of the of measuring the error. What do you think could be a different way of measuring the error? Again, I'm looking for answers. I'm looking for a different function phi by which okay, so you have I don't see your name, so you have basically a way of raising your hands. Okay, so Shin, yeah, Shinman, am I saying the name correctly? You can unmute yourself and talk. Or somebody else, yeah?
NMSC?
Gal. Again?
NMSC,
What
normalized.
is NMSC?
Normalized means square error. The same
How
function
do you normalize it?
by the, how do you quantify the size of xi, if it's L2 or L1?
Well, let's continue, Gal. Let's continue this conversation. What is L1?
L1 is the sum of the absolute values of the elements in the vector.
Okay, so what Gal is suggesting is something else. Let's wait with the weights. Okay, we'll get back to them. But what Gal is suggesting is saying something like that. I don't want the L2. I would like to do something like that. Am I correct? This is what you meant? Yep.
I'm using the same psi of MSC, just divide each element by the L2 of xi.
So what you're saying is that it would be like summing over or all the the squared, but dividing by xi minus theta, something like that.
Or dividing by xi L2 of xi, xi squared.
Dividing by xi.
I think he
Okay,
means
so this
divided
is
by L2 of x.
Dividing by L2 of x, I see. So this would be dividing by xi squared. Okay, this is an interesting idea. It would indeed weigh the my numbers, but let me give you now an example. Let's take this example. Assume that in Apple everybody is getting more or less something like Tim Cook's salary. Okay, so everybody is getting a really high salary, and now there is one poor guy that was just hired, and he's getting really low salary. I mean, he's getting something which is really close to zero. If I'm using a measure like that, then what would happen is that the close to zero salary would influence the rest of the numbers. And I assume that what you would get is something which is awfully biased in a very similar way to the one that we try to avoid to begin with. Okay, so I'm looking for other ideas.
The median.
The median. So Barak rescued us and said the median. So how would you get into the median? So median or chetzion בעברית, median. Thank you, Barak. So how would you get to the median? Anyone has a, remember that to the average, the way that we got the average is by defining the sum over xi minus theta squared, okay? And then taking the derivative with respect to theta, what we got is the mean. So now I'm looking for another way for something which would not be called MSE, but rather something else, from which I can somehow extract the median. Anyone has any ideas? This is a really important point. I mean, if you understand that, then the rest of the course, I'm not saying it would be trivial, but it would be bearable.
I think you have to sort it.
Again?
I think you have to sort it and take what's in the middle.
Sorting the numbers, again, please say your name before you talk because I don't see. So sorting the numbers and taking the median is a way of finding the median. But this is not a way of defining an error measure that would yield the median. This is what I'm looking for. I'm looking for a penalty, a way of measuring something that would account for all the xi's and would find for me theta, and theta would then be the median. So let's go backwards a little bit. Okay, let's go to our original penalty and let's observe what is going on in this penalty. Remember that I'm measuring L2, okay? L2, we called it L2. This is the squared of the difference between each and every xi and my representative function, representative numbers. So if I have a lot of points at one point, and I have one point far, far away from it, and I'm looking for a blue point that would represent all of them, then obviously if I square the distance, and I'm not talking about the median, if I take the square of the distance, then obviously it would shift the point, the blue point, closer to the far away point, because squaring it is, in a sense, weighing it by a large number. So instead of squaring this difference, instead of squaring these epsilon i's, these errors, what other idea do you have besides L2?
L1.
L1, Barak, yeah? Okay, so Barak suggested L1. So let me rescue you from this misery. Instead of squaring, instead of summing over the squares, what I will do is I will take the square root of that guy. And in fact, it would be equivalent. Let me just, Mark, sorry. Next time, just say say your name and so the only one that raised his hand here is Mark, and from some reason.
Oh yeah, I found the button.
Okay, so instead of summing over all the squares, xi minus theta, I will sum over all the absolute values of these errors. Okay, so summing over all the absolute value, and let me write it in a different way for my sake. Remember that the square is a well-defined function. It always returns a positive number. So taking the square root of the square of a function is in fact identical mathematically to what is written here at the top, okay? But this is an analytic function. This is something that I can take the derivative. If I take the derivative of this guy with respect to theta, I'm getting something, okay? So this would be my new phi. And if I'm taking my new phi, the derivative of my new phi with respect to theta, I should be getting something. So what is this something that I'm getting? Anyone has any ideas?
Probably the median.
Dan? This is Dan was
I
talking?
mean, I assume because we've been having all this talk up, I assume it's going to be the median or something related.
Why? So no, but I was not asking about the, yeah, it would be the median. Thank you, Dan. I was building the expectations toward. So it would be the median. But in order to get to the median, I would like to ask you, what is the derivative of this psi with respect to theta? Okay. Now you have all done your calculus in high school, and you have done your basic calculus in the university. So please try to take 2 minutes. We have it. And take the derivative of this guy with respect to theta and tell me what you get. 2 minutes. So this is a 2-minute break. Take the derivative of sum of xi. I hope that you have a pen and a paper near you. Minus theta. And in order to make it simple, make it square here and square root here. So, any ideas? Let me give you a hint. Throw away the constants. So obviously there is it's a fraction, and there is 2 here and 1/2 here. So throw away all the constants. Just keep the whatever is left.
Is it the sum of the signs of the?
Thank you, Barak. So what Barak is saying is this is the sum of the sine of what? Of xi minus theta. Okay, this is what you meant?
Yeah.
And let me tell you, sorry, let me just tell my other TA that took over obviously my iPad that I cannot answer right now. Okay, so what is going on if we are taking the derivative, then in the denominator what we will have is basically the absolute value. Sorry, let me just try and do that again. Is the absolute value of xi minus theta, as long as it would not be 0. And here I have xi minus theta. Okay, this is what you got. Okay, this is what you will get if you, what you have here is basically this guy squared. So in fact, this is equal to nothing but sum over the sine of xi minus theta. Now remember, I have my numbers, and my numbers are ordered from smaller to larger, and I'm looking for a representative number such that the sign of my difference between, so I'm looking for n number, okay, this red dot, so that the difference between this red dot and all the blue dots would sum up to 0. So this would have obviously a positive sign, and this would have a positive sign, and this would have a positive sign. Okay, so all the ones on the left would have a positive sign. At the other end, all the points on the right would have Again, who forgot the minus sign? Somebody forgot the minus sign. So at the other end, on the left, you'd have all the negatives, okay? So here you have negatives. Now, in order for all the pluses to cancel all the minuses, you immediately understand what you have to choose. It would be if n equals to 2k, where k is some integer plus 1, then what you will have to do is choose the median. Now, if n is equal to 2k, I mean, if 2k, sorry, if n is not an even number, but rather not an odd number, but rather an even number, what would you choose in that case? Any ideas?
One of the two in the middle.
Again, I didn't hear.
One of the two numbers in the middle.
Yeah, so Alexander said that I need to pick up any point in the middle between the 2 points that are, I mean, if this would be, if I would have k points here and k points there, in fact, selecting any points between this k and k plus 1, this k and k plus 1 objects or numbers would be a valid representative. I mean, it would yield a derivative which is equal to 0, which would be a minimum of this number. Okay, so this is the idea, and so let's go into first of all, let's do the analysis properly for the mean square error. So if I'm taking the sum over the xi minus theta squared and taking the derivative, this is what I'm getting explicitly. And now what I will do is I will, instead of theta, what I will do is insert in the average. Okay, we learned that the average would give me the minimum value. So this is just opening the brackets. Okay, this is just opening the brackets here. Since theta minimum is a constant, I can take it out of the summation. So what I would have here is theta minimum, and here I would have the average again, and here I have theta minimum squared. So at the end, multiplying theta minimum by theta minimum, I mean, we know that the minimum is the average. What I would get is the first term, which is the sum over the squared values minus, here I have minus 2 and here I have plus 1, so minus the squared of the minimum, and this is writing it explicitly. Now, how do I know that the subtracting the sum, the square of the sum minus from the sum of the squares is always greater than 0? I mean, how would you prove this part? It's trivial. Anyone has any idea? Usually when I'm saying it's trivial, it means that it requires some effort.
Cauchy-Schwarz.
Cauchy-Schwarz is one way of looking at that, but let me show you a very trivial way of looking at that. Remember where we start from, okay? We start from this guy. This guy is nothing but xi minus theta, means some number, okay? Squared. What do I know about square numbers? They are always greater than 0, okay? So this guy would always be greater than 0. So yes, I can apply Cauchy-Schwarz to this equation and prove it. But since I'm starting from something which is always greater than 0, obviously subtracting from the sum of squared, the square root of sums would be always greater than 0. Okay, so obviously the error would always be greater than 0. So it is indeed pleasing to see that the average of the numbers is an optimal representation of the loss. And now what we'll do is we'll get to the different loss, and the different loss that I was talking about. Now, what I suggest is continuing this lecture, since you're sitting in your homes and you have your coffees and everybody is happy. I suggest that we'll continue this lecture without taking a break, unless anyone really needs to go to the toilets or something like that. So just raise your hand and I will try to accommodate. So instead of making it quarter of an hour and quarter of an hour, we'll just make it an hour and a half. Now, So this is it. Usually what we'll do, as we have 3 hours lectures, so what we will do is we'll give 1 hour, then half an hour break, then another 1 hour. Okay, this is what I like to do, because then it gives you, I mean, it doesn't break the flow in the middle, and it's 2 hours sitting in a row is can be an effort. Okay, so now we go into our other penalty function, which was the absolute value of each, and taking the absolute value of each and every error. And this is the definition of this error, and it is called mean absolute deviation, or MAD, or MAD. And this is the loss function, and it's called the L1 norm. Why? Because it is minimizing the absolute value. If you think about it, the L2 was summing over something squared, and the L1 is summing the elements in a one norm. Okay, so I'm taking the absolute value. Immediately you know what would be other types of norms that if you'd like to use them. So this would be the L1 norm of this vector, of the error vectors. So it would be the sum of the absolute values. And we immediately see that if we take a derivative, and this is something that Barak showed us, what we are basically summing is over the signs. And I forgot the minus at the beginning. Okay, so if I equate it to 0, I can now throw away the sign, and I can throw away the constants. And what I'm looking is exactly placing my representative number in the middle. Okay, so this would be the median. Now, a question to the audience. What would be the complexity of finding the median? Remember, for the mean, what we had to do. So assume that you have a set of numbers, and the set of numbers is not ordered. Okay, so you have one number, another number, then another number, and you have to find the median of these numbers. Not sorting them, but rather just finding the median. What would be the complexity of finding the median? Ideas?
I guess n log n, because
So
like
the
to
obvious
sort.
answer by Mark would be n log n. Okay, because first of all, you need to order all the points, and then once you order the points, you get to the center, and finding the central point is constant time. So if somebody is giving you the points in an ordered fashion, it would be a constant time. But in order to order them, you need to resort to the ordering procedure and find a way of putting them. Now, this was indeed what the first algorithms people in computer science thought. They thought that indeed finding the median in a list of n numbers, and a list of n numbers would take n log n. And they tried to prove it. And it appears to be that you can do it in order of n. It's a beautiful algorithm. I will not. You take a bunch of 5s, you split your numbers into 5s, you order them, and then in constant time, and then you take the points in the middle, and you build some hierarchy. The algorithm is not very complicated, but it is an order of n algorithm. So finding the median is not only more robust, but can be done in linear time in the number of points that you have. I don't know if it's so relevant today where we have all the parallel computers that can do all the n log n algorithms in constant, I'm joking obviously, in constant time, but if you really need a fast median solver on a sequential computer, know that you can do it in constant time. Okay, so obviously the loss function is challenging because we don't have the derivative at 0. Especially when, I mean, if you look at this function for a single variable, it looks like that. So if the mean square error function for a single variable was something like that, this is how it looks for a single variable. And in the 0, when my xi or x is equal 0, I have a number. Okay, this is my entry to my penalty function. But again, we used our definition of the square and the square root in order to take a derivative. By some abuse of notations, we have been able to write it as a sum of sines. And the question is, where is it equal to 0? Gives us, I mean, the birth is nothing but the median. Okay, so now we have the median as a result. And now assume that somebody is giving us the points in an order fashion. So x1 is smaller or equal to x2, etc., etc. And I have 2 points in the middle. And now the question is, what happens when capital N, when the number of numbers that I have is an even number, or what happens when it's an odd number? So when it's an odd number, the answer is trivial. What I do is I pick up the points in the center. And as I think Michael said, or Alex said, if I have an even number, an even number of points, so if, for example, I have 20 points or 50 points or 100 points, then what I can do is I can choose theta to be any number between the 2 points in the middle. So let us prove this, this intuition in the following way. First of all, we write the absolute value as follows. As the now, in order to get the absolute value, what I need to take is this subtraction of theta from xi and multiply it by the sign of this guy. Okay, this is something that I can do. This is a definition. Okay, if I do that, and I write my MAD penalty in a different way, what I can do is for any k, okay, for any k, picking up theta between any k would yield the following penalty. So this is for any theta. This is not the optimal, this is any theta. By the way, you will get all the lecture notes afterwards, so feel free to read them. I will also probably give you every time the lecture notes for the next lecture, so you should be able to go over them and give clever answers if you like, or just come surprised to class and not give clever answers, or give clever answers as you think about them. So I can write my MAD penalty as follows. Sum all the positives. Okay, so this would be, so I have my numbers and I've selected my representative theta to be somewhere here. So what I do is I'm summing over all the signs of these guys, okay, plus times the sign, so it would be positive. And then I'm also summing over all these guys, okay? And obviously it would be a positive number. So this is a way of looking at the absolute value. If this would be, I mean, if xi minus theta would be negative, I'm just switching the order of the subtraction, and it would guarantee that this one would always be greater than 0. And the same goes for all the points that are from to the right to my theta. This would always be larger than 0. Okay, so this is a way of writing this penalty. And now I'm continuing to open this this equation. So what I have here is k times theta. This goes from, let me just get rid of that, change the color. So from this guy, what I will be getting is k times theta. Now I also have from summing over this part is n minus k thetas that I'm getting with a minus sign that I'm getting from here. Now what I'm left with is nothing but summing over my minus xi, which I'm getting here, and summing over my xi, which I will be getting here. So I have two portions which are unrelated to theta. So when I will take a derivative with respect to theta, these guys will vanish. And I have another term which does relate to theta. Now, looking at this guy, this is nothing but an integration of all the numbers. I mean, I'm summing all the numbers. So if this would be theta, theta is always my red numbers. So I'm basically summing over all my xi's until theta. Okay, so this would be this guy. So this would be an integration, and I'm calling it sk. Okay, so sk would be the integration or the sum of all the numbers until a specific index k. Okay. Now, what is this guy? This guy is summing all the numbers from a specific k. So what I can do is sum all the numbers until my n number. So this is xn. So I can sum over all the numbers, which would be Sn. And from my Sn, I can subtract all the numbers, which are all the k numbers, which are smaller, which is nothing but Sk. Okay, so what I have on the right here, let me get rid of that. So what I get on the right here is nothing but this term. It would be the sum over all the numbers, and I'm subtracting Sk, and I'm subtracting it twice. Okay, and again, this is a constant number. So what do we do with this term? What I will do with this term is I will try to prove to you that if I'm taking the derivative and eventually choosing the median, it would go down until I'm getting to the median. It would be equal to 0 only if I'm choosing the median, and then it would go up. Okay, so this is choosing theta. So this would be more or less a graph of phi MAD. Okay, it's a linear function as a function of choosing the theta. So this would be my theta. I'm now playing with theta, and I'm plotting the value of phi mad. So if I'm choosing my theta to be between x0 or x1 and x2, I would get some slope, and the slope would be 2k n minus 1. And since 2k over n for k smaller than n divided by 2, since this part is negative, then the slope between these 2 points would be negative. Okay, and I continue. Now I'm choosing my theta between x2 and x3. Again, this guy is still smaller than 1, so the slope is still negative. And I continue my journey, and I continue my journey, etc., until when? Until I will get a 0 here. Okay. Then what would happen? Then k would be, k would be larger than n divided by 2, and therefore this part would be larger than 1, and therefore the whole part would be positive. So the derivative with respect to theta, to add to my theta afterwards, would be positive. So again, this is between k x. Assume that n is 10, so this is x6, and this would be x7, so the slope would be positive, and this would be between x7 and x8, so the slope would be positive. Okay, and in fact, you can see that the slope is increasing, so it would be a function which is monotonic, and then it would be like that. So the more we deviate from the median, the larger the slope of this function would be. Okay. So again, what we are doing is analyzing the MAD. So we see that the MAD is a piecewise linear and decreases when k is smaller than n over 2, and we see that it is equal to 0. I mean, the derivative is equal to 0, or the value of the function is constant when 2k over n is equal to 1, or that one, and then it increases. Okay. So the minimum of this function is attained at a specific k if it satisfies this equation, and immediately we know that it needs to be the point in the middle. So So it is if I have an odd number of numbers, and if I have an even number of numbers, it would be exactly in the central number. Sorry, so for the odd number of numbers, it attains its minimum at the point itself. If I have an odd number of numbers, or in the interval between these two guys, if I have an even number of numbers. Okay, so now I can define the median. So the magic here is that the median was realized from defining a loss function, a penalty function. Now the median, it is trivial in a sense to do it for one-dimensional signals, okay, for numbers in the plane, in R. But now think of what would happen if you no longer have points along a line, but rather points in the plane. What would be the definition of a median there? What would be the definition of a median in other domains? I mean, if you have many variables and then you would like to, it would be much easier to first of all define the loss as we did here, rather than start speculating about how should I generalize the whole notion of a median. So thinking on the problem from a mathematical point of view about L1 and L2 would make the difference, okay? And this would be the sort of axiomatic way to go. And again, when you train your networks afterwards, I mean, when you grow up and you continue your journey in deep learning and you, office hours, somebody was asking about office hours and maybe I was, so office hours would be upon request. So just email me or send me, just upon request. And usually it would be after the recitation. So if the recitation is just after the, I don't remember, I think the lectures are on Monday, not after the recitation, so after the lecture. So on Monday, I think we have 3 hours, and then it would be, I don't remember when we stop, it would be either, this would be the default numbers, but then the best way would be to get in touch by email, and then if you have more urgent questions, I can answer it on the fly. Let me see if I'm not missing anything else. Yeah, so somebody mentioned about the 0, and then Barak said that it doesn't matter because when it is 0, it is 0. Okay, so next, what do we do next? So we have the mean absolute deviation, and now assume somebody once mentioned that we could probably compute the median or the MAD using a different way of a loss function. Let's wait with that, okay? Let's wait with that. So now let us see if we can, like we did in the MSE, somehow write an expression for the error when the when I'm choosing the optimal solution. So now I plug in the median into the MAD loss, and what I'm getting is that the first part is nothing but, the second part is nothing but subtracting the integral of the whole from the integral over twice the integral over half of the sequence. Okay, this is a constant number. No matter what I do, this is what I'm choosing, and k here would be the k in the middle. Okay, and now the question is, and this is what I'm getting actually as my error. So it would be this guy that could vanish minus this guy, which is a constant. Okay, so if I'm choosing n to be 2k, to be so this would be an even number. So n would be an even number. Then the error would be nothing but what I'm getting over here. So remember that in the why? Because this one would vanish, this one would go away. If I'm choosing an odd number, so this would be an odd number. I mean, n would be an odd number. I have an odd number of numbers. choosing the median would give me something which is a little bit more complicated. But again, let's zoom onto the even guy and see that this is more or less similar in nature than what I would have received in the previous case, in the MSE case, where we subtracted the sum of squares from the square of sums. Okay. Sorry, the other way around. The sum of we subtracted the square of sums from the sum of squares. Okay, so this is more or less it. I mean, I'm subtracting twice the integration to the middle from the integration of the whole. Okay, so this would be my error. And now I also know that this guy is greater than 0. Why? Because we started from summing over the absolute value. Okay, so obviously this would be always larger than 0. Okay, next. So this is an analysis of the sum of absolute value. So what do we note? This is nothing but, I mean, summing over all the numbers is nothing but the average of all the numbers. This is the average of only the half part of the numbers. And obviously, since we are looking at numbers which are smaller than the median, then the average of these guys would be twice the average of these guys, which is twice this number, would be smaller than the average of all the numbers, okay? Because what would happen is that all these numbers would drift, would push my average, the average of all the numbers from being the center of gravity here to the center of gravity here, okay? And this is nothing but the average of all the numbers up to half point between the 2 points in the middle, especially if I have an even number of points. So if this would have been x, okay, and this would have been x, k plus 1, and this guy is sitting exactly in the middle, so this would be the sum towards the guy in the middle. Okay, so I hope that I've convinced you that something good is happening here. So what do we have until now? What we have until now is somehow realized at best, and the best is either the MSE or the MAD, that gave birth to the average or to the median of a list of numbers. Okay, and then we recover the mean and the median as being the optimal with respect to the measure itself. Now, what we would like our psi function to be robust with, and our estimators to be robust with, is permutation of the numbers. So I told you that the numbers are ordered, but assume that somebody is giving me the numbers in an unordered fashion. I would like my phi of that is getting epsilon with respect to the same number, and epsilon with respect to the second number, etc., to be agnostic to the way that the xi are ordered. So assume that somebody is giving me a permutation. Okay, so what is a permutation? Assume that I have my indices 1, 2 to n. Okay, and now somebody is giving me a permutation. What is a permutation? Usually I consider it as a matrix that would first of all do the first selection. So it would, for example, give me, I don't know, 7 to be the first number. Okay, remember how I multiply a matrix with a column with a vector. Then I have another one. I'm picking up the first element, etc. And then I have n, and I don't know, here at the bottom I have 3. So somebody is giving me, so I have my line of numbers, but now this would be x1, this would be x2, this would be x3, and the numbers are giving me in an unordered fashion. It is very important that the penalty function would be agnostic, would be invariant with respect to the order of the numbers. Why is it so important? It is important because if tomorrow somebody is giving me not points on the line for which you can apply your n log n or an algorithm to order them or find the median. If somebody tomorrow is giving me some points in the plane or some other realizations, I would like my penalty function to be invariant with respect to the way that these coordinates are being fed to me, or the order of points are being fed to me. So it is really important to be agnostic, to be invariant with respect to the way that the numbers that my objects are being fed into the penalty function. And what can I say about the MSE and the MAD? And the MAD. Do you know anything? I mean, does anyone, are they invariant to permutation of the object that they are receiving?
Yes, they are.
Yes, they are. Said who? Gal?
Yes.
Okay. So Gal is saying that yes, they are, and is actually correct. And you can prove it. I mean, it's quite easy to prove. I mean, when you sum over, let me just get some points, some space here. Come on. When you sum over some numbers, square, or you sum over the absolute value, it doesn't matter which one you fit first into your summing, I mean, into your summation, the order does not matter. So in the specific case of MAD or MSE, we are lucky to have a permutation invariant or a permutation invariant penalty function. Okay, let's go to some other way of looking at observing functions, of observing numbers. Assume that now, instead of just giving me the number, somebody is also giving me a weight. So I think it was Michael or Gal or somebody else who at the beginning suggested to also add weights to the game. Okay, so now somebody is telling me, look, this guy is very important. When you weigh his salary, you should multiply it by 5, by 10, by whatever. And the question is, how do we do that? I mean, how can we overcome this problem of having a weight for each and every number? And the answer is a weighted mean square error. Okay, so it's again the same mean square error, but now each and every subtraction I multiply by my weight. And obviously, instead of just dividing by n, what I do is divide by the sum of all the weights. So let me take the simplest example at which wi is equal to nothing but 1. In that case, I would get the original problem, and this is nothing but the unweighted MSE. But if, for example, wi is different for each and every xi that I'm getting, then I'm getting a different way of a different penalty. Now, since this is a really trivial way to take the derivative off, so what I can do is take the derivative of this guy with respect to theta, exactly as we did before. And what I'm getting is I have a constant number here, and I can get rid of this constant number here. I mean, this guy is constant, and when I equate my differentiation to 0, I can get rid of that. And the derivative of that part is nothing but 2 times wi that multiplies xi minus theta. And when I open that, okay, so again, I can throw away the constant, I can throw away the 2, and what I have is sum over wi xi that should be equal to sum over theta times wi. Okay. Now remember that theta is a constant. I can take theta out of the summation here. Okay. So if I'm taking theta out of the summation, what I'm getting is nothing but theta equals to the optimal theta would be equal to whatever is written here at the bottom. Okay, so you have here the solution for the optimal theta. We also write it as the minimum theta. This is with respect to the weight w. And this is the argument that I'm minimizing here is theta. So I'm writing R min of psi MSE weighted MSE with respect to theta. And the optimal guy is nothing but sum of all wi times xi divided by the sum over all the weights. And again, if by any chance I've chosen my weights to be equal to 1, what I'm getting is the trivial average. But if the weights are more important for some rather than the others, then I'm getting this weight here, and this is called weighted sum. Okay, so this is a generalization of the mean, of the weighted mean of the numbers. Can you think how to do it with the median? Anyone, any idea? How would you treat the fact that the penalty here is squared and thereby it penalizes a lot? We call it outliers, חריגים בעברית. Okay, so the question is, what would you do if I'm telling you, look, here you don't need to put the square, but rather the absolute value? I mean, you can do that. Okay, you can do that, and you can think of you'd get something which is similar to the median. Okay, let's not get into it right now. Okay, let's analyze what happens when I plug the optimal theta into the weighted sum. So again, exactly as before, what happens here is that I'm plugging the weighted. So instead of the weight here, I'm plugging, instead of theta here, I'm applying the weighted optimal theta, which is nothing but 1 over the sum of all the weights times the weighted xi. Okay, so if I plug it here, let's first of all open that one before I plug it in. So this is the first term, it's wi times xi, then I get -2 times the division times this guy. Okay, and then I have a sum over this guy plus the square over the w omega. Okay, and here at the end I have the sum over the wi. Now, what happens here if I have sum over all wi divided by sum of all wi? I can basically cancel these two guys. Okay, and what I have here is nothing but the theta omega mean square, and what I have in the middle is theta omega mean, but this guy is nothing but theta omega mean. Okay, so I have two theta omega mean squares, and at the end what I'm getting is exactly as before. I'm getting the sum over the weighted squared minus square over the weighted sum. Okay, so the weighted average of the square data, okay, this is the weighted average of the square data minus the squared weighted average of the data is the loss for the optimal choice of theta. Okay, and it reminds us what we have seen before. Now, everything we talked about until now can be casted into a probabilistic setting. Instead of a fixed wi, what we need to somehow invent is a process that replaces w by relate w to some probability. Before we do that, let's revisit the whole notion of, okay, so let me first of all comment about the MAD and tell you that you can do that and work out this example in details for the MAD. And now there is a different question of for which weight would the optimal MAD be equivalent to the optimal MSE. So the question is, which weights should I use in order to find that? And let me give you a hint. At the beginning of the lecture, somebody actually suggested, or at least I thought was suggesting something like that. And the solution to this problem is called iterative reweighted least squares. And by iterative, I mean that I'm playing with the weight every time, and I'm feeding a new weight. And if I'm playing with the weight and I'm using the right weight, at the end of the day, if I'm converging to the global minimum, I would get the MAD, the median, as a solution, okay? Why is it important? It is important because in some cases, it is very difficult to minimize and to optimize numerically for the L1. And we would like to somehow ask the question is, how can we relate it to an L2 optimizer? And apparently we can. We can find and define weights that would optimize an L2 problem, and then find a new problem and new weights, and then optimize a new L2 problem, and then find the new weights and a new problem that would find. And if we solve this L2 problem enough times, and if we converge to the global minimum, then we are guaranteed to have this optimization solved. Okay, so this is an interesting problem, and I do suggest that you look into it. If you can't solve it, then I will show you the solution. Okay, so now assume that my x's are in a box. Okay, so there is a box. There is no political connotation to the fact that I'm writing Bibi here. It's a black box, and in the box there are numbers, and I'm picking up these numbers. Okay, so and here I have a genie. So each and every of these elements has an index. So this would have index 1, this would have index 2, and as a whole I would have n indices. Okay. And there is a genie here. Okay, and the genie, let's write the genie here. And the genie is blindfolded. He doesn't see what is going on in the box, and is picking. So he put his coronavirus mask on his eyes, and he doesn't see anything. And he picks a number, and this number is being he picks an index, and this index. So he picks an index, and we call this index W. And from this index, the realization of this index, what we get is a number. And this number is called X of W. In a moment, I will show you this process in a more orderly fashion, but this is more or less the picking up the right number out of a given set of indices. First of all, I'm picking up the index, and the number behind this index would be my representative numbers. If you're confused now, wait a little bit, it would be clear later. So the numbers are in a box. Formally, we define the variable, which would be the index. So the variable W is a value between 1 and n, which means, by the way, that you can pick up the first index more than once. Okay, there is a probability of choosing the first number. Okay, and let's assume for a moment that the probability is uniform, and therefore the probability of choosing a specific index is 1 over n. So if I have n indices, the probability of choosing the number I is equal to nothing but 1 over n. So we called a capital X of W a random variable. Okay. And what we have is that the realization, the probability of having the random variable equal to xi is equal to 1 over n in our specific case. Or it could be any other weight or any other number if we choose not to have a uniform distribution. So now we can ask, what is mu? Okay, so instead of theta in the non-stochastic case, in the statistical case, we are asking what is mu that would best represent the values of the random variable X of W. Okay?
Expectancy.
Again, the expectancy. Thank you. So this would be the expectancy. בעברית we'll call it the משערך. So XW would be the expectancy, of course, if we define it properly. So it would take for all the probabilities of taking the various possible values. So what would be the best representative for the variable number XW? So let us now define the expectation. Okay, so what we do is we define the error to be nothing but taking the random variable, subtracting the representative mu from this random variable, and writing it in a probabilistic manner would be finding the expectancy or the expectation of with respect to W of X minus mu. And remember that mu is a constant, is the number that I'm looking for. Okay. Now, what is the expectancy? Is taking the probability of XW being equal to Xi times Xi minus mu. Okay, so this is the realization. So I'm summing over all the numbers, over all the indices, again as before, subtracting from Xi mu and multiplying it by the probability of XW equals Xi. If I do that, I know in my case, I know that the probability of choosing any I is uniform, and therefore I can plug in 1 over n. So again, remember that this is only for uniform distribution. And what I can do, now remember that I have the second term here is sum over mu of 1 over n. Mu is a constant that I can take out of the summation. So what I have here is nothing but mu of n divided by n, and this is nothing but minus mu. And the first part is nothing but the average, okay? The average of all the numbers that I have. So if I select mu to be the average, what I get is that the expectation of the error would be nothing but 0, okay? So the expected error would be 0 if I select my mu of x to be the average. Okay, so we get 0 expected error if we select mu to be the average, and mu is nothing. In a more general case, if I don't have uniform distribution, then this is how I can write it. Mu, or the expectation, would be nothing but xi times the probability of choosing the ith number. Okay, so this number is called the expected value, the expectation of the random or the expectation of the random variable xw. Okay, so what about the process of minimizing the MSE, the mean, the sum over the square or error? Okay, let's write it. So now what we'll do is minimize. We'll take 10 more minutes with your permission, okay? What we'll do is we minimize the expectation, the square of the expectation error, okay? So what we do is we look for the expectation of xw minus mu squared. So what we do is we need to multiply this term times its probability. So we can write it explicitly. I mean, this is just opening these equations explicitly times the probability. And what we get is the square here, minus 2 mu times xi times the probability there. And here we have mu squared times sum over all the probabilities. Now let's bisect it. Let's dissect it term by term. What is the sum over all the probabilities? Over all probability of I? What do we know from probability theory? Gal, yeah?
1.
1. So this was? Who was that? It was Gal or Mark?
Mu squared.
Yeah? Again, so this is equal to?
1.
1. Thank you. Okay. What else can we say? So this is equal to 1. So let's let's remember this. I mean, so we can just remember, we can just delete this term and keep this up to this point. Now, what else can we say? So now this is equal to 1, not only for the uniform distribution, but for any distribution. Okay, this is something that we know for all distributions, the probability is equal to 1. So therefore, what we have is that we can write the previous summation as sum over, let me go over the previous summation. Okay, this is what we had. We had the probability of xi times the probability of my x, it would basically be, I'm calling it pi or pxi, and this guy would be nothing but the mu, okay, and this one would be equal to 1, and therefore at the end of the day what we are getting is this equation, okay. So I would get that the error would be nothing but what is written here. Okay, so this would be choosing the average, the expectation. This would be Wx. And if by any chance I'm choosing mu to be equal to mu x, what I would get is that this guy would be equal to, let's wait. Let's do that. So first of all, what would be the optimal mu? Taking a derivative with respect to mu would give it this guy. And at the end of the day, I would get that the mu optimal is equal to nothing but my mu x, nothing but my expectation, okay? So I know that choosing the expectation would be indeed the optimal representation for my probabilistic, in my probabilistic setting. And now the question is, what would happen if I plug it into this error? So if now I would plug it into this error, what I would basically get, let me see. What I would basically get is this equation, okay? Here at the bottom. I don't want to rush too much into, so again, what we did is if we select mu x to be my expectation, which is nothing but sum over xi times the probability of my of selecting my random variable to be xi, then it would zero the expectation error, and it would minimize the min, the expected value of the squared error, okay? Now, there are other names to this guy. We'll relate to them, variance, etc. Again? So I said before, so I win.
Variance.
Yeah, so it would be indeed the variance, but now it should give you a really good intuition of what the variance is. So the variance can be written in this crazy manner, but if you recall what we did for the non-stochastic case, which is basically defining the MSE error, and at the end of the day, if we plugged in the optimal solution, what we got is a subtraction of sum of the squared minus a square of the sum. Then here the variance is exactly the same idea. It's basically subtracting from the second order moment. So another way of calling it is moment. So it's subtracting from the second order moment the squared of the first order moment. Okay, so this would be second, and this would be first. Okay, so summing over all the squares would give me the second order moment. Summing over the sum would give me a first order moment. Let's see if I'm not missing anything important. So again, the expectation is called the expected value or the mean or the first order moment. Okay, first order moment. The sum of the squared is called the second order moment, or the distribution of my random variable. And this guy, the analog of the MSE, is called the variance. Okay, variance גם בעברית. order of the random variable. Sometimes we denote the variance, which is the minimum mean square error by its mean. And so if we, in some cases, we write it as this guy. And if we take off the square, then it's called the standard deviation. So the square of the variance is nothing but the standard deviation. This is how it is called from obvious reasons. I still have one moment. Okay, let's leave it at this point for the next lecture. I don't want to overload you. I will give you, I mean, I will send Tom and the slides, and they will distribute it for you. And yeah, and please, if you have any questions, now it's time to ask them. I mean, let's leave a couple of moments for questions. So please feel free to either raise your hand, and if I will see that there is balagan, I will use my linear algorithm to order you. Any questions? Or if you have any other expectations from this course that I was able to demolish.
How are we continuing with the tutorials and the lectures?
So the tutorials would also be online until we have other options. I mean, I don't like it. I really like to come and present things on the board. I can do it. I mean, I like to see faces. I like to communicate with people. I would like to isolate the clever guys in this course and then continue talking to them, and if there are interesting problems that go beyond this course, to show you interesting problems. So again, this is my view of but for the time being, I don't think that we have any chance, any other alternatives. And
I meant more regarding the, because of the swap of the first tutorial and the first lecture.
Can you move closer to your mic, or?
Because right now it was supposed to be the first tutorial. So how are you going to make it up?
So this is an excellent question. I think that Tom already answered that. What would happen is that the next lecture would also be given by me. Tom, correct me if I'm wrong. And then you will have the first recitations, the first irgun, and then we'll continue as regular. So at the end of the day, you will have 13. I will not overload you. So we will have 13 lectures and 13, and I think also 13 recitations.
So the next tutorial is next week. Okay,
again?
next Wednesday.
So next week I'm giving my lecture, and then you would give your recitations. I don't remember. Yeah. So at the end, probably what we'll do is we'll see if one of us is going too fast. Then what we'll do is we'll switch one. I mean, I will give Tom one of the lectures, and this is how they will be able to. We'll do load balancing. But in order for the recitation to the exercises to be more informative, I did want to go over the basics of the course as first lecture. So this is my fault, if you will. Other questions?
Do you maybe have a desired background in probability that you want us to have, that you want us to review on? Or can I?
So yeah, the answer is yes. I would. I mean, let me tell you what I prefer that you know. I would like you to know what is the expectation of probability. I would like you to know what is an autocorrelation matrix and a correlation matrix of a set of random variables, but I will explain it from scratch. So if you don't know what it is, I will present it in class. So yes, I would like you to know what is an autocorrelation matrix. Why? Because it is really important. I mean, if somebody is telling you that he knows what is PCA, principal component analysis, and at the end of this course you would like to call yourself a data science engineer or data scientist, without understanding what is an autocorrelation matrix or a correlation matrix, you will not be able to do PCA properly. However, it is a very simple and trivial idea, more or less along the way of moving from constant weights into probability. I mean, it's basically the same idea, if you like. Okay, so if you have, in this specific case, if you have two random variables, then they are independent in a sense, then you can write their joint probability as multiplication of the probabilities. If they do depend on one another, then there are other ways to do that. So yeah, this is, I would really like you to understand a little bit what is an autocorrelation matrix. So yes, this is the answer. At the end of the day, and let me tell you why it is important. If you have a function or a realization of some process, and you would like to say something clever about it, so it's either given to you as a set of numbers or a set of functions, and then the question is, how can you encapsulate this knowledge into a filter, into an estimator? And the way to do it is to resort to probability. I mean, they have tools and they have vocabulary to deal with these structures. So not much. I mean, I'm not a probabilistic expert, but a little bit is something that would benefit a lot from.
Just,
Omer,
I'd like to add, the basics to understand all this, and Ronnie will explain very well, is just what is a random variable, what is a probability distribution, how to compute the expectation, what it means. And if you understand the basics, you can easily understand what is autocorrelation, how it relates to PCA and everything, and that will be done in class. So just go through your basics.
Yeah, so we will go to the
Okay,
basics,
thank
we'll re-explain it, but if you don't have the background, I mean, my suggestion is to go over the background again. I mean, my suggestion is also to go over your calculus. I mean, you need to know how to integrate, you need to know how to integrate by parts. In this course, we don't take directional derivatives, but this is something that you should know. This is more or less it. So if there are no further questions, then again, I will leave you to your busy Zooming day. Yeah, algebra is also important. Yeah, you need to know how to diagonalize matrices, how to multiply a matrix by a vector, what is the meaning of eigenvalue and eigenvector. This is really, really important. Okay, thank you very much, and we'll see you Monday.
Thank you.
Thank you.
Thanks.
Thank you. See you on Monday.